Hi, I'm Rob Hoyt, founder and president at Tether's Limited Inc. And I'd like to tell you about work we're doing to develop OSAM technologies to enable in-space services. The work we're doing is motivated by a desire to help create a robust and sustainable in-space economy. Now, there are a number of different markets that various ventures are pursuing for creating in-space businesses, but each of these by itself doesn't create a fully functioning economy. We see OSAM as the keystone for tying together these multiple different markets to create a sustainable economy where we can acquire resources in space, transform them into things of value, and then provide them and provide services to other customers. About the journey we've been taking to develop these capabilities. And we've been very fortunate to be able to work with a number of sponsors and customers at NASA and other government entities to develop and mature these technologies. We started this journey off by working under a grant from NASA's Innovative Advanced Concepts, or NIAC program, where we developed a OSAM architecture called SpiderFab for in-space manufacturing and assembly of large space systems. And then we were able to transition that effort to a number of follow-on projects, mainly funded by NASA's SBIR program, to develop the key component technologies needed to implement that SpiderFab architecture. And more recently, we've been able to transition those efforts to flight demonstrations under programs such as STMD's tech demo missions and other opportunities. So when we talk about in-space services, we are working in three main areas. In-space servicing, where we're looking to create benefits such as enabling missions that require persistent maneuvering, as well as support the long-term sustainability of operations in low Earth orbit. We're also working on in-space assembly of modular platforms and integration of upgrade payloads. And the main benefit of that will be improved responsiveness to market and mission demands. And then in-space manufacturing, where we're looking to carry raw materials into orbit and transform them into structures, apertures, arrays, and even entire systems. And the primary benefit of that will be increased performance per dollar for a number of different space missions. Within the areas of in-space servicing and assembly, we're working on a number of different technologies. Many of them are working to lead towards a small, low-cost robotic servicing and assembly vehicle that we call Leo Knight. Leo Knight will be an ESPA-class robotic servicing vehicle, and it's sized for cost-effective in-space integration of ESPA-class payloads, as well as servicing of small satellite systems. And it integrates a number of our component technologies, including robotic arms, tool changers, a water-based refuelable propulsion system, and the Cylon multi-agent collaborative control methods, all of which I'll talk about in a few minutes. A key element of the Leo Knight and many of our other in-space manufacturing and assembly technologies is a compact but very capable robotic arm that we call the KRAKEN. The KRAKEN arm is designed to stow into a very compact form factor so that it can fit onto a nanosatellite or fit into an express rack payload on the space station. One of the key aspects of the KRAKEN arm is that it integrates very precise torque, sensing, and control capabilities, and that enables it to operate in a mode that we call active compliance, which we'll talk about more in a few minutes. The current baseline configuration of the arm, which is being designed to fit into the MANTIS express rack locker, will have a roughly 1 meter reach, 7 degrees of freedom, and mass about 5 kilograms. But the KRAKEN design is modular and adjustable so that we can readily optimize it for a variety of different missions. The MANTIS payload is a roughly suitcase-sized payload designed to fit into a space station express rack. The MANTIS integrates a KRAKEN robotic arm, several tools, and control avionics to enable teleoperation of experiments and other hardware on the space station. So the idea behind MANTIS is to offload menial and repetitive duties from the astronauts and enable researchers on the ground to perform those duties. So the main idea is to greatly improve the scientific throughput on the space station. The KRAKEN arm on the MANTIS payload will be operating within the crew volume on the space station, so it needs to be designed to ensure astronaut safety. So the arm integrates very precise torque sensing and control with very fast feedback capabilities, so it can be operated in active compliance mode. What this means, as illustrated in the test video on the right here, is that as the arm operates, it can be programmed with very precise torque limits so that if another piece of equipment or an astronaut were to move into its way, the arm can sense the obstruction and actively comply to it. So, for example, if it were to run into an astronaut, the astronaut could just push the arm out of the way, and then the arm will go back to doing what it's programmed to do. For in-space assembly and manufacturing applications, this capability will also be very important because it will enable the arm to controllably apply a precise amount of force or torque to a client spacecraft. This will enable a very small, lightweight arm to manipulate very large, heavy objects. To enable the KRAKEN arm on MANTIS and on spacecraft applications to use multiple different tools, we've also developed a compact tool change interface called ARTIE. ARTIE is an androgynous connector, so it can be used both as a mounting point and as a tool change interface. And it integrates power protection, safe to mate, safe to connect functionalities to enable safe connection of multiple different tools. To enable in-space assembly of modular space systems, as well as integration of payloads onto existing spacecraft, we've developed the AXON payload and module connectors. The AXON is also an androgynous connector. And an important aspect of its design is that either side of the connection can secure or separate the connection, even if the other side of the connection is unpowered. And that will enable a space system to release payloads or modules that have gone defunct. Axon Connector also integrates a novel cover mechanism that protects electrical or optical components from the space environment. Space systems that are assembled or manufactured on orbit will require new kinds of control methodologies to account for challenges such as changing moment of inertia, multiple robotic agents, and distributed control architectures. So Tethers Unlimited has developed the Mosaic toolset. Mosaic is a Simulink-based environment for developing and testing ConOps for satellite assembly, satellite servicing, formation flight, and modular space systems. Shown in the center is a Mosaic simulation of a distributed attitude control method where 3 small satellites are spaced along a 10-meter long truss, and those 3 satellites work collaboratively to maneuver the system as well as to mitigate vibrations that maneuvers induce on the structure. Shown on the right is a Mosaic simulation of development of the Cylon algorithms for collaborative control of multiple robotic arms and multiple robotic agents. In this simulation, a 2-armed servicer vehicle is manipulating a client spacecraft and refueling it using a remote fueling tank. You can see that the simulation accurately captures the full multi-body dynamics of the system. Hi, I'm Rob Hoyt. Now, when we have modular space systems and multiple robotic systems working together, we need a way for these multiple entities to communicate together in an efficient manner. So we have developed a mesh network solution called SwiftLink that enables multiple satellites and multiple agents to set up a peer-to-peer mesh network and exchange data using standard IP-based protocols. Now let's talk about in-space manufacturing technologies. For in-space manufacturing, one of the first questions is, how do we get the materials used for the manufacturing? So we have been exploring approaches for taking materials available in space and recycling them to create feedstock for manufacturing processes. The Refabricator is a express rack payload that's currently on the space station. It is designed to demonstrate recycling and 3D printing of polymeric materials in the space environment. Additionally, we have been working with NASA's in-space manufacturing program to develop technologies for a system called FabLab. FabLab will integrate capabilities for 3D printing metals, subtractive manufacturing, and inline inspection of the parts so that FabLab can produce metallic, mission-critical parts with the precision and reliability needed to serve mission-critical applications. Additionally, we have been working to develop technologies for in-space manufacture of high-performance, very thermally stable truss structures. Shown on the left is an early prototype of a device called the Trussulator, making a 10-meter long carbon fiber truss structure. Currently, we are collaborating with NASA and Maxar to prepare a flight demonstration called MakerSat. The MakerSat experiment will fly as part of the Spider experiment on the OSAM-1 mission in a few years. The MakerSat payload will fabricate a high-performance carbon fiber composite boom with a length of 10 to 20 meters from the spacecraft. And as it does so, it's going to measure its straightness as well as measure its stiffness and other structural properties as it is making the structure so that we can compare the performance of the on-orbit manufactured beam to comparable beams that we manufacture on the ground. The current status of that effort is we have completed CDR and we're on schedule to deliver flight hardware next summer. So essentially the MakerSat mission will be demonstrating in-space manufacture of the 2x4s that we need to build space infrastructure, such as thermally stable platforms for giant telescopes or structures for space stations and other space exploration craft. Over the past few years, we have also been working under funding from DARPA to develop a payload called OrbWeaver. The OrbWeaver payload will ride on an ESPA ring, and after the ESPA ring has done its job of releasing secondary payloads, the OrbWeaver will actually chew up most of the material of the ESPA ring and feed the aluminum chips from that into a smelting and casting system. The smelting and casting system will then transform those chips into hexagonal reflector segments, and the robotics on the OrbWeaver payload will then assemble those hexes together to create a large, high-performance antenna reflector, and then integrate that reflector with radios and other RF components so that the system transforms into a high-throughput tactical SATCOM satellite able to close many high-speed data links to VSAT terminals on the ground. My name is Rob Hoyt. My email is hoyt@tethers.com, and I look forward to answering any questions you might have. Thank you.